So hi everyone, wait for a couple of more minutes and then we can start. So hi everyone, I think we'll just wait for one more minute and then we can start. So, hi everyone. I welcome you to this live session number 13. So, this is an extra, or you can call it a recap. Just a second, I'll just admit some participants first. So, just a second. So, hi everyone again. Welcome you all to this live session number 13. This is the extra, or you can call it a recap session of the course. So, how I'm going to approach this? So, basically, what I've done is I have picked some questions that I've already shown in previous live sessions, only 3 or 4 questions. Some questions that were given to you in your assignments, I'll show them, and some questions that I have taken up from other course, other materials, other from other sources. I will be discussing them. So, in short, it will cover some 10 to 15 to 16 problems covering most of the aspects of the course, and in this way you can just get a recap of some of the fundamentals of this course, that is a digital circuits course. So the problems were chosen such that they had something new, or the problems that I had already discussed in my live session. I picked them because I found that they are important from the examination point of view, from the concept point of view, and also the assignment problems I found which were interesting or just needed to be looked again from the perspective that they were quite covering lots of aspects from the conceptual point of view. So I'm discussing them again. In short, this is a recap session. So any doubts, any time, I'll just give you time after the question is solved. You can ask me your doubts. And also in this session, I'll ask you. Typically, I used to give you 3, 4 problems to solve first, and then I used to show solution. Here, I will try to at least give you 5, 6, more than 6 problems to solve. Then I'll show the solution. In that way, you will just know where you are lagging and how you have to approach a particular problem. Mostly, those problems will be the unseen problems that you haven't seen, and the problems that you have seen, I will just take a look at back again. So, without further ado, I'll just start. So, we are bound to give this introduction every time. So, my name is Musa Rafiq. I'm a PhD student in the Department of Electrical Engineering at IIT Kanpur. So, I'm a TA for the course Digital Circuits. The course is taught by Professor Shantanu Chattopadhyay from IIT Kharagpur, and this is the last session of the course. So, this is a question. I think it was in this year's assignment. So, it asks us the output Y in the circuit below is always 1 when, so we need to figure out when the output of the following circuit is 1 and what are the conditions that need to be satisfied so that the output is always 1. So what I will do is, if you remember some of the students that were also present earlier in my live sessions, I typically divide the circuits like this, and try to give them the labels. In that way, my computation gets easier. At least I'm able to figure out the things that are happening. So the chances of making a minor mistakes are less in that way. So I'm calling this output, that is output from this AND gate 1 to NAND gates 4, 5, and 6. So the output from this AND gate 1, I'll call it X1, and from this I'll call it X2. This is my X, this is my X3, and this is my X4, and this is my X5. And finally, for the final output, I have the Y, so I don't need to uh, name it. So now, what is my X1? So my X1 is equal to, it's a NAND operation between P and Q, so it's PQ bar. Then my X2 is the NAND operation between Q and R. Then I have X3, which is a NAND operation between R and P, so I'll call it as PR complement, right? Now what I'm left with is this X4, so I need to write X4. This X4 is a NAND operation between X1 and X2, right? And now I'll plug these values here. So this is PQ complement QR complement, and then it's the whole complement, right? So using which law? De Morgan's law. I'll just open it up. So it's PQ complement whole complement plus QR complement whole complement. So this is ultimately equal to PQ plus QR, because A complement whole complement is A. These were the points I was just trying to mention. That is, we'll recap some of the points that are quite important, like De Morgan's law, this property. And now I have x5. So what is this? This is simply your NOT gate using a NAND gate. So x5 will be equal to x4 complement. So that is PQ plus QR complement, right? And if you use De Morgan's law, it will be PQ complement dot QR complement. Now my final Y will be equal to, it's a NAND operation between x5 and x3. So I write x5 and x3 and my NAND. So my x5 is PQ complement dot QR complement, then dot x3 is my PR complement, then whole complement. And now I'm using De Morgan's law. It will be PQ complement complement plus QR complement complement plus PR complement complement. So it is ultimately equal to PQ plus QR plus PR. So this is my final expression. And if you look at the options, and you need to write down your answer like that. So if you carefully examine this, when is this y equal to 1? So when any of the terms PQ plus QR plus PR is 1, because in our operation, so any of the three terms, if 1 is 1, so it will be 1. So either PQ should be 1, QR should be 1, or PR should be 1. So this thing is satisfied when two of the three inputs are 1, then output is always 1. So see, if P and Q are 1, this term is 1. I don't care about R. So if Q and R are 1, so this is 1. I don't care about the other two terms. And if P and R is 1, so this term is 1. I don't care about Q. So my output will always be 1. So the condition for output to always be 1 is any of the two or more inputs should be 1. So option B. Now I have a question here. So do you know which gate this is? We have a name for this type of gate. The whole circuit that is shown, where two or more inputs should be 1 for the output to be 1. We associate a name to this. Anyone? Anyone has any idea what this is called? So this circuit that you see here is, we call it a where function is where output is 1 when two of the three inputs are 1, two out of three inputs are 1. So it's called a majority gate. You can look it up. So a majority gate is, it is an input gate where n is your odd, and where more than half of the inputs are 1, the output will be 1. So we call it a majority gate. So it is a three input majority gate where output will always be 1 if two or more inputs are 1, right? So you can look this up, this majority gate. This is useful, this majority gate useful from approximate computing perspective, where these adders and multipliers are made using these uh, majority circuits, where we don't care about the computational accuracy, we take about the approximate answer these solutions from this majority gate. So I thought just I'll give you an idea about this. So now we have another problem at hand. So I would like you guys to do this first. I assume you haven't seen this type of problem because I have taken it from another set. So it says that design a 4-bit odd parity generator using a 4 is to 1 multiplexer. Consider AB as your select lines. So I'll give approximately 5 minutes. It should not take more than 5 minutes to solve. So you have this question. I'll repeat it again. It states that design a 4-bit odd parity generator using a 4 is to 1 multiplexer. Consider AB as your select line. So I'll just give you 5 minutes. Till then you can solve this. Full adder carry output. Yes, full adder carry output is like that. Yes, you're right. Yeah. AB plus BC plus EA. Yes, yeah, that is here also. But I was just thinking about the gate. Yeah. So this is your question two. So kindly do it, and then I'll show the solution. So to the participant that joined late, you can try this question within 3-4 minutes, and then I'll show the solution. So this is a question. It states that design a 4-bit odd parity generator using 4 is to 1 mux. Consider AB as your select line. So has anyone done it? I see one of the student has written the answer. Apart from that, anyone else? Are you guys doing it? Uh, do you guys need more time to solve it? Anyone else with the answer? So if you are do it parallelly, I'll assume you are doing it parallelly or there was a problem with solving. So let me just show the solution. So the question asks us to design a 4-bit odd parity generator using a 4:1 mux where your AB is your select line. So I have my A, B, C, D, and here is my F, which is the output of the 4-bit odd parity generator. So it will so what is the function of odd bit parity generator? It will give us the output 1 when we have to make the total number of bits as odd. It will give output 0 if the bits were already odd. So I'll just start writing the all cases 0 1 0 1 0. Just wait. So any question? Someone has raised the hand. Okay, you can type it in the chat box, no issues. Just a moment, someone wants to join the meeting. So now let's just fill the output of this. What should I say? The truth table for this parity generator. So here the number of outs are 0 even, so 1 will be output. Here it's 0, here it's 0 again, here it's 1, here it's 0, here it's 1, here it's 1 again, here it's 0, 0, 1, 1, 0, and here it should be 1, here it should be 0, here it should be 0, and here it should be 1. Now let's see. The question asks us to design it using a 4:1 mux where A, B are my select lines. Now I will use the Corno map. Here I have my A, B, C, D. So this is 0, 0, 0, 1, 1, 0, 1, 1, 1, 0. Similarly, here it is 0, 0, 0, 1, 1, 1, 1, 0. And if I have to fill it, it's like this. You can check it. It's like this only. So A and B are my select lines. So these are my select lines. So when AB is 0, 0, I0 will be selected. When AB is 0, 1, I1 will be selected. When AB is 1, 1, I2 will be selected. And when AB is I3, sorry. And AB is 1, 0, I2 will be selected. Right. So these are my select lines here. With AB being 0, 0, I0 will be selected. So when AB is 0, 0, that is I0 will be selected. So I0 is equal to, so what will I0 be equal to? I0 will be equal to this plus this. So I0 will be equal to, when AB is 0, 0, I0 will be 1 when when we have this case C bar D bar plus C D. So this is I0 will be C XOR D. So when AB is 0, 0, I0 will be routed and I0 is equal to C XOR D. When AB is was 0, 1, so I1, so it will be C D bar plus C bar C, so it's C bar D plus C D bar, right? So it's C XOR D. Then I have I3, which is for the case 1, 1. So I3 will be equal to again C XOR D. Similarly, I2 will be equal to same case for I1, C XOR D. So I0 is equal to C XOR D, I1 is equal to C XOR D, I3 is equal to C XOR D, and I2 is equal to C XOR D. So option A, as rightly pointed out by some of the students, is the correct answer. Now we have another question, which I think I shown in my week 1 lecture, but I thought this is a really important question. So it states that consider the equation 1, 2, 3 to the base 5 equal to x to the base y, where x and y are unknown. The number of possible solutions are, so we are given this number 1, 2, 3 to the base 5 equal to x8 to the base y. So we need to figure out how many possible solutions are there. So this can be written like this. So 5, 0, 1 to 5 square multiplied by 1 plus 5 into 2 plus 5 raised to power 0 multiplied by 3 plus xy plus y raised to power 0 multiplied by 8. So this thing is equal to 25 plus 10 plus 3 is equal to xy plus 8. So xy is equal to, sum it up, so this is 35 plus 3 is 38 and 38 minus 8 is equal to 30. So xy, the product of x and y is 30. So now let's just look at the possible solutions. So the possible solution can be x equal to 1 and y equal to 30. So this is one possible solution. Another possible solution is x is equal to 2 and y is equal to 15. Number third solution is x is equal to 3 and y is equal to 10. Right. And fourth can be x is equal to 5 and y is equal to 6. But this cannot be the solution. Can you tell me why? X. No, no, no. I'm just saying x equal to 5 and y equal to 6 cannot be the solution to this equation. Why? So 123 to the base of 5. So I'm not getting your point. Can you please repeat or frame it in some other words? So x equal to, yeah, continue. Hmm. So that is after substitution. That is true because of, I am just saying that it is not a solution. I'm just saying 100% it's not a solution. Just by looking at the equation, how can I say this is not a solution outrightly? Anyone else? So basically, the problem here is y equal to 6. X can be equal to 5, but y cannot be equal to 6. Why? Yes, right. Exactly. So if a number cannot be in a number system, number cannot be greater than the base of the system. So if it's 8, so y has to be greater than 8, right? So that is the criteria. So whenever you write this equation, so x y equal to 30, given y is greater than 8. So this is your criteria. So the number of possible solutions are 3 only. So option A is the correct answer. This question I found it really interesting. This question I have at least shown it. This is the fourth time I'm showing this question to, mm, twice I've shown it to previous two classes and twice I've shown it here. It's a really good question. Pretty much easy, but good question from a conceptual point of view. Then I have my another question, which says that the logic functionality realized by the circuit shown below is, so we have these NMOS transistors where A and B are A are connected to drain, B is connected to the gate, and we have B bar connected to the gate of another NMOS. So we need to figure out the logical functionality done by the circuit, right? So A equal to 1 is my high, that is high voltage, and A equal to 0 is the ground. So let's just make the truth table and deduce what logical functionality it performs. A B is equal to 0 0. So A is equal to 0, so this will be ground, and B is equal to 0. So this transistor, because at the gate it's 0 volt, it will be off. Then B bar is the high voltage, so this will be 1. So Y will be connected to ground, Y will be equal to 0. Then A is equal to 0, B is equal to 1. So A is equal to 0, so A is again connected to ground, B is 1, so this transistor will be on, B bar will be off. So again Y is connected to ground via this transistor, so Y will be equal to 0. Then I'm A equal to 1, Y B equal to 0. So A is equal to 1, so here I have high voltage, B equal to 0, so this transistor is off. And B bar is equal to 1, so this transistor will be connected to ground via this transistor, so it again be equal to 0. So here I have 1, here I have 1. So A equal to 1, B equal to 1, this transistor will be on. B bar equal to 0, this transistor will be off. So Y will be connected to A, that is a high voltage, so it will be 1. So the functionality realized by the circuit, as you can see from the truth table, is a AND gate, where my output is only 1 when both of the inputs are high. For all other cases, it's low. So option D is my correct answer. Now, this is a question. It states that reduce the circuit, find the reduced circuit for the following circuit. So we are given this circuit and we need to deduce the reduced circuit. So what we have here is, let's just call this as x1 and this is your x2 and this is your y, or should I call it f. So f is equal to x1 and with x2, x1 is equal to A B bar C bar. So x1 is equal to A plus B bar plus C bar, and x2 is equal to A C bar, sorry, C and B bar. So A is x2 is equal to A plus B bar plus C. So my F is equal to A plus B bar plus C bar, and with A plus B bar plus C. Now I'm opening this up. So A dot A is A plus AB bar plus AC plus B bar A B bar, B bar is B bar. So and then we have B bar C. Then this thing is AC bar plus B bar C bar. Then C bar C is 0. Now I have my expression like this: A plus A B bar plus AC plus AB bar B bar plus B bar C plus AC bar plus B bar C bar. So I'll take A common. So I get 1 plus AB bar, 1 plus B bar plus C plus 1 plus B bar plus C plus B bar. Then I'll take B bar as common. I'll get 1 plus C plus C bar plus A bar C bar, A bar C bar plus. So this thing should have been gone to there. So you could have taken AC bar, and in here you will get AC bar. So ultimately this will be equal to, doesn't matter whatever is in the bracket with the OR operation, this is equal to 1 only. So this is A plus B bar. So my F got reduced to A plus B bar. So F can be realized like this: A and B goes to the NOT gate, and then it's the XOR gate, and I have the function. So A plus B bar. So option D is my correct answer. Now question 6, I would like you guys to do first, then I'll show the solution. Or okay, let me just show it outrightly. So I need to determine the inputs of given 4:1 mux to make the output xy plus z, where x is MSB and z is LSB. So use xy as your select lines and z as your input variable. So I need to design, I need to make this circuit for output expression xy equal to z, xy plus z using the 4:1 mux, where xy are my select lines and z is my input variable. So first of all, let me just get to the expression that we need to implement. So q is equal to xy plus z. So q is equal to, we have to write it in standard SOP form for the implementation using a mux. So what I will do is I will write xy z plus z complement plus z times x plus x complement, right? So this will be equal to xy z plus xy z bar plus xz plus x bar z. This is an elaborative way. You can even have the shortcuts to directly write down the sum of midterms, but better to do it like this. So xy z bar, then this is xy z, I'm just skipping one step, plus xy bar z plus x bar y z plus x bar y bar z. So ultimately my answer, this sum of product will be summation of, there are some redundant terms, you can look into that, 1 3 5 6 7. So the question now reduced to implement this expression using a 4:1 mux, where my X and Y, which are my MSB, and the right term towards the MSB as my select lines, and the Z, which is the LSB, is your input variable. Now I have Z bar and I have Z. Here I have D0, which are my input lines, D1, D2, and D3. So this is the implementation I'm trying to construct. Now the question here is, this is 0. So where will be the 1? Here or here? Yes, because right now it is the LSB that is the input variable. If it was the MSB, I would have written like this: 0, 1, 2, 3. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. Now I'll encircle all those terms which are present in the expression. So this is 1, this is 3, this is 5, and I have 6, 7. So from here I'll get Z, I'll get Z, I'll get Z, and here I'll get 1. So D0 is Z, D1 is Z, D2 is Z, and D3 is 1. So this is the expression I got. So that is option A, which is my correct answer. So this was your question number 6. Now I think we can move forward to question number 7 of this recap session. So question number 7 states that convert a T flip-flop to D flip-flop. I had already given this problem in my I think week number 6 tutorial, but I'll like to repeat it again because these conversion problems are really important. This one is not that difficult, but I want to give you the flavor of it. I mean to say how to approach these problems. So I have jotted down these 5 points which you should remember while doing these conversion problems. So number one point is you need to identify your required flip-flop, your available flip-flop. Then you need to make a characteristic table of the required flip-flop. Then you need to make an excitation table of an available flip-flop. Then write down the Boolean expression of the available flip-flop. And finally, draw the circuit. So here, before we move forward, we have to identify available and we have to identify required. So available is my T and required is my D. Just a second, someone wants to join the meeting. So as I was saying, we need to convert T flip-flop into D flip-flop, and we can use it if you remember these 5 points for a conversion problem. There may be other ways also, but I used to do it like this, so I thought I'll share it with you. So first you need to identify the available and the required flip-flop. So in our case, as the question asks us, convert T to D. So available is T and required is D. Then you need to make the characteristics table of the required flip-flop. So required flip-flop is D. So here I have Qn, here I have D. So 0 0 0 1 1 0 1 1. So you know that Qn plus 1 is equal to D for a D flip-flop. So it will be 0 1 0 1, exactly the input. Then I have to make an excitation table of available flip-flop. So excitation table is formed between Qn and Qn plus 1. So it is 0 0 0 1 1 0 1 1. And excitation table of the T flip-flop is like this: 0 1 1 1 0. Now I need to write the Boolean expression for the available flip-flop. So it's T. So it's simply I don't need to elaborate it like this. So T is 1 1 for this case, that is the XOR operation between Qn and D. You can simply write down T is equal to Qn XOR with D. So your flip-flop will be something like this. So T is your available, here is your XOR gate, this is D, and the other input is your Qn. So in this way you can always approach a conversion problem of the flip-flops, where one flip-flop is made available to you and you need to convert that flip-flop to other flip-flop. So this was just a, what should I say, uh, overview of these conversion problems, a brief overview. Using this, you can always do other problems as well. Now, let me just show another question of this recap session, that is question number 8. So I would like you guys to do first. So I haven't given so options aren't available anyways. So what I will do, for sanity, I'll just ask you to write the output expression of y1 in the chat box. So what is y1? When I'll show the solution, I'll show the output expression for all of them. But right now, I want you guys to write the expression for y1, or do it for all other cases, y1, y0, and v. So the question basically states that simplify the Boolean expression for customized priority encoder given in the table below. So find the expression. I forgot to put the options here, but anyways, you can do it. Write the Boolean expression for y1, y0, and v. So you have written y1 is equal to enable d1 bar d0. I think you are forgetting something. Kindly check it. Kindly check it once. It's partially correct. You are missing some term. Any other? So if you don't know how to write d1 bar or d or any bar, so you can like d1 bar like this. So in case someone is having any trouble writing bar and so on, complement, you can write the complement like this. So has anyone else done it? You can write your solution here. So y1 is equal to e d2 d1 d0. So I think you are forgetting a complement on one term. Maybe check it once. So it should be e d2 plus e d1 bar d0. So let me just show the solution. So I expected other students to do also. This was a very simple problem. Are you guys doing it? Yes. So yeah. So now let me just show. So what we have here is we first do it for y1 and let's draw the K map. So there are four variables. This is your en, this is your d2, this is your d1, and this is your d0. So this is 0 0 0 1 1 0 1 1 1 0 0 0 0 1 1 1 1 0. So your y1 is 1. Check this case. So y1 is 1 when en is 1 and d2 is 1. So when en is 1 and d2 is 1, and for whatever be the value of d1 and d0, we don't care. So it will be always 1 when en and d2 are 1. So it will be like this, right? And also y1 is 1. Y1 is 1 when En and D2 are 1 0, when En and D2 are 1 0, and D1 and D0 are 0 1. So like this. So now if I use the K-map solving technique, so it will be like this, forming this chord and forming this pair. So Y1 will be equal to En D2 plus En plus En, what should I say, En D2 bar, yes. En d2 bar because of this zero factor, and it's 0 0 0 1, so it's d1 bar. So y1 will be equal to en d2 plus d1. So y1 will be equal to en d2. So I'm just missing something. Y1 is en d2 and en d2 bar, en d2 bar. So d2 plus d2 bar d1, d2 bar d2 bar d1. Yes. Then I have y0, this thing. Y0 is 1. Let me just draw the K map first. So yeah, this is y1 is equal to this term. This is wrong. So this is en, this term coming from the pair. So this is en. Then it's what should I say? 0 1 is uh, 0 1 is d1 bar d0. Yes. So y1 will be equal to en d2 plus d1 bar d0. I got confused because the term coming from this pair is en dn d1 bar d0. I just took d2 there, so it's en d1 bar d0. So now y0 will do. So en d1 d0, and this is d2 0 0 0 1 1 1 1 0. 0 0 0 1 1 1 1 0. Now y0 is 1 for this case when en is 1 and d1 is 1. When en is 1, sorry, so it's y1 y0 is 1 when en and d2 are 1 0, en and d2 are 1 0 like here, and e1 and d2 are 1 0, and d1 is 1, so d1 is 1, and we don't care about d0, so this will be 1 and 1 for both the cases, because d0 don't care, we don't care about the value of d0, whatever be the value of 0 d0, it will be 1. So for 1 0 1 it is 1, for 1 0 1 it's 1, and for 1 0 1 0 is also 1. Now y0 is also 1 for this case, 1 0 0 0 1, so 1 0 0 0 1 is this case. So now minimizing this, so we get these two pairs. So my y0 is equal to en d2 bar, en d2 bar, and the term coming from this is d1, sorry, d0, and the other term is en d2 bar d1. So y0 will be equal to en d2 bar d0 plus d1. And finally we have for the v, we can draw this k map like this. Again similarly following the same strategy, en d2. Now v is 1 when e and d2 is 1 and d1 and d2 are don't care, so it's 1 for this complete row. V is 1 when e and d2 is 1 0 and d1 is 1 and don't care on d0, so it's like this, and it's also 1 for 1 0 0 1, so it's like this. So I can construct three chords, 1 2 and 3. So my answer will be, I'll just skip some steps, it is equal to v is equal to en d0 plus d1 plus d2. You can check this, it is your answer. So v is my e and d0 d plus d1 plus d2, y0 is my e and d2 bar d0 plus d1, and y1 is my e and d2 plus d1 bar d0. So this was the answer. So one of the student has written y0 is equal to e and d2 bar d1 plus d2 bar plus d2 bar plus d2 bar d1 d0. No, I think y0 y0. You kindly check it. I think it's wrong. So is it clear? Now moving to question number 9. It states that initial contents of the following flip-flops are ABC are 0110. What are the contents of ABC after two clock cycles? So I have clock cycles like here. I write it like here, and here are my contents A, B, C, E. So for first cycle, this is 0110. This is the first cycle, initial. Now this E bar is connected to D of input D of this first flip flop, that is A. So for the first clock cycle, this will propagate. So this will be 1, and for all other cases, it will be like this because they are propagating. So 0 will come here, 1 will come here, and 1 will come here. And for the next clock cycle, now E is 1, E bar will be 0, so it will be 0, and this one will come here, this 0 will come here, and this one will come here. So it's 0 1 0 1. So option B is the correct answer. Yes, one of the student has done it. This type of question are pretty easy, but the moral was this, the main agenda of putting it here was because you can expect these type of questions, maybe some different flavors of these type of questions in your exams or any other competitive exam. So I find this question important from that perspective. That's why I put it here. Now I would like you guys to do this question first, and then I'll show the solution to this question. It states that consider the equation 5p364 to the base 8 and 5afq to the base 16. The value of p and q are dash and dash. You need to find out the values of p and q, and I'll just give you 5 minutes. You should be able to do it in 5 minutes. So should I repeat the question or you guys get it? So after 5 minutes, you can write your answer in the chat box. So anyone else? Only one of the student has given the answer in the chat box. Is anyone else doing? So, to the participant that has given the answer option A, so I'd like you to answer this question. So, would you have been able to do it if the options were not available, or you just use the options and got the answer? Okay, okay. No, I was just confirming because that's one of the way. Yes, that's one of the way surely, but there's another way that is the more appropriate way that to do it. Yeah. Yeah. So sometimes in competitive exam you usually get MCQs. So in that way, using options method will save you a lot of time. But if this was a direct answer type question, fill in the blanks type of question. So I was just confirming. So other students, what about other students? So you got this expression, this 512 p minus q is equal to something like that, and then you plug the options and checked which of the option was correct, right? Is that how you guys did, or maybe some other way? Okay, yes. Anyways, I'll just show the solution because this question is really interesting. So let's just take this expression because if you equate these two sides and solve, you get a one equation for two variables that 5.2p minus q is equal to something, right? So you have two variables, one equation, so you can't just solve it outrightly. So what some of you guys may have done it or maybe not, you can just plug these values and check which one of the equation satisfies and you can write your values. What if options were not available? So there is a way how you can do it. So let's just take the left hand side of the equation, that is LHS. Let's just take LHS and RHS simultaneously. So LHS is equal to this thing. So it is 5. So 1, 0, 1, 2, 3, 4. The reason I'm coming from this side because of the space issues. Otherwise, whenever you are doing these type of questions, start from this 4 into 8 raised power 0 type. So 5 multiplied by 8 raised power 4 plus p multiplied by 8 cube plus 3 multiplied by 8 square plus 6 multiplied by 8 plus 8 multiplied by 8 raised power 0 multiplied by 4 is equal to the LHS right hand side 5 multiplied by 16 raised power 3 plus a, that is 10. 10 multiplied by 16 square plus 15 because f is equal to 15. 15 multiplied by 16 and then I have q multiplied by 16 raised power 0. So what I will do, I'll try to convert these powers of 8 to the powers of 16 and then I will compare the LHS and RHS and see make the coefficients equal. So 8 raised power 4. So 8 raised power 4 is simply equal to 16 cube. You can check 8 raised power 4 is equal to 16 cube. So I can write this thing as 5 into 16 cube plus 8 cube. So you can write this 8 cube as 8 16 square multiplied by 8, you can write this. So 8 cube is your 256, right? So 8 cube is your 256. No, it's not 256. It's 512. So 8 cube is your 512. You can write it 2 into p into 256. So 256 is your 16 square plus 3 into 8 square. So now I have to write 16 to, so I have to write it into 16 raised power 1. So 8 square is 64 divided by 16 you get 4. So it's 3 into 4 16 raised power 1 plus it's 48. 48 divided by 16 is 3. So 3 into 16 raised power 1. And you can write this 8 raised power 0 as 16 raised power 0 because both of them are equal to 1. So you can write like this 16 raised power 0 and then the RHS will remain same. Now you write it 5 into 16 raised power 3 plus 2p into 16 square plus this is 12 plus 3, so it is 15 into 16 raised power 1 plus 4 into 16 raised power 0 is equal to 5 into 16 cube plus 10 into 16 square plus 15 into 16 and then q into 16 raised to the power 0. Now comparing these terms, so you can see 5 into 16 cube, 5 into 16 cube, 15 into 16, 15 into 16, and here is your 4 and here is your q. So from symmetry, q is equal to 4, you can check, and 2p is equal to 10. That implies p is equal to 5. So p is equal to 5, q is equal to 4 is your answer. Any doubt? Binary, but you binary like 2 power 2. Yeah, yeah, because right now I had a liberty because 8 and 16 are quite related to each other, so that's why. Maybe sometimes you cannot, maybe not here we you could sometimes, maybe sometimes there was not an option, huh? Right? Yeah, yeah. Sometimes maybe you cannot. Yeah, there will be case. I think there will definitely be cases where you can't do it like this. So that time maybe that is not a question, but this is how you can do these types of questions. So I just thought I'll give you an idea of this. Otherwise, using options you would have already done it, because I have seen in some of the competitive exams where you can see using options. There is this term called I don't know what is that called, substitution, directly substituting the options and you get the answer. So was this clear? So now I have this question which states that the truth table of XY flip-flop is shown below. Design the flip-flop using JK flip-flop. So this is a conversion problem. I think I've shown this in my live session, one of the live session. So I would like you guys to do it. Okay, now let me just show. Okay, okay, do it first, then I'll show the solution. So one of the student wrote in binary, then for P, one of the student wrote in binary, then for P grouped in 3 and for Q grouped in 4 on either side. Yeah, that's another way. Definitely, you can do it like that. And that's the beauty of these live sessions. I also got to know you can do it like this, because in examinations you try to find multiple ways of solving the question. So by the way, one of the students has written option B, Suresh. It is for this question or for the previous one you had written? No, I'll suggest kindly check it once. So let me just show the solution. So we are given the truth table. We are given the truth table of this XY flip-flop, and we need to design it using a JK flip-flop. So the points I told you to, first need to find the available flip-flop, that is JK, and the required, that is this X. We don't know what this X is, so this is the required flip-flop XY. Then you need to write the characteristics equation of XY flip-flop. So here is the characteristic table of the XY flip-flop. When XY is 0 and Qn is equal to 0. So when XY is 0, 0, Qn is equal to Qn bar. So 1, 0. When XY is 0, 1, it's 1, 1. When XY is 1, 0, it's 0, 0. And when XY is 1, 1, it's Qn bar. Right? Now this was the characteristic table of the XY flip-flop. Now we have to write down the excitation table of a JK flip-flop. So when Qn is equal to 0, Qn plus 1 is equal to 1, and Qn is equal to 0, Qn plus 1 is equal to 1, it's 1 comma x. It's 1 comma x. When it's 1 0, when it's 1 0 is x comma 1. When it's 0 1, it's 1x. When it's 1 1 is x 0. When it's 0 0, it's 0x. When it's 1 0, it's x1. When it's 0 1, it's 1x. And when it's 1 0, it's x1. So like this, 1x x1, 1x x1, 1x x1, 1x x0, 0x x1, 1x x1. So this is my characteristic excitation table. Now we need to write down the equations for this thing. For J, so here I have x, y, and qn. So it's 0 0 0 1 1 1 1 0 0 1. So it's 1x x1, then it's 0, then it's x 1x. So you can make this chord and you can make this chord. So J is equal to x bar plus q, sorry, x bar plus y, x bar plus y. Now for k, it's x 1 0 x, then it's x 1 1 x. So you can make this chord and this chord. So k is equal to your x plus 0 0 0 1 plus y bar. So your j is x bar plus y, your k is x plus y bar. Your j is x bar plus y and k is your x plus y bar. So option D is the right answer. Now I have this question. It states that the following synchronous sequential circuit is designed with a JK flip-flop and a T flip-flop with J is equal to A plus B bar, K is equal to A bar plus B, and TB is equal to A. If the initial state A and B is 0 0, then find the sequence of states visited by the circuit. So we need to find the transitions made by the states of the circuits. Given J is equal to A plus B bar, K is equal to A bar plus B, and TB is equal to A. So you know, for a JK flip-flop, we have this equation Qn plus 1 is equal to J Q bar plus K bar Q, right? This is your characteristic equation for JK flip-flop. Here Q in place of Q it's A, so it's A n plus 1 is equal to J Q is equal to A plus K bar A. Then your J is equal to A plus B bar, A plus B bar times A bar, and your K is equal to A bar plus B, A bar plus B whole bar coming out from this, and A. So A and A bar is 0, so it's A bar B bar, then it's plus, using De Morgan's law, it's A B, it's A B bar dot A. So finally your expression reduced to A bar B bar plus B bar, taking B bar common, so it's B bar 1 plus A bar. So ultimately this is equal to B bar. Similarly, your Bn plus 1 is equal to, so Bn is the output of this T flip flop, and you know for a T flip flop, Qn plus 1 is equal to Tb XOR with Q. So it's Tb XOR with B. So it's Tb is your A. So it's A XOR with B. So Bn plus 1 is A XOR with B, and An plus 1 is B bar. Now I'll just write it here. A and B are my present states, and here I have A n plus 1 and B n plus 1, right? So 0 0 0 1 1 0 1 1. So when my A and B are, so when A is n is 0, An plus AB is 0, A and B are 0, An plus 1 is B bar, so B bar is complement, simply complement of B, and Bn plus 1 is A XOR with B, so it's 0 1 1 0. Now we need to find out the transitions this circuit makes. So I'm at first 0 0, right? So I am at 0 0, so I'll be going to 1 0. Now I'm at 1 0, so the next state I'll be going to is 1 1. And when I am 1 1 1, I'll be going back to 0 0. So this is a transition this circuit will make, that is from 0 0 to 1 0 to 1 1 to 0 0. That is option B. Yes. Mhm. Mm. So this is a transition. You are not looking JK flip flop alone. So you need to these equation needs to satisfy this flip flop. So my available is J and K. So I have to give input like this. So this is my JK and here is my X. So it should be J is equal to, I am giving it like this, X bar plus Y. So this is my J and K is my X plus Y bar, right? And this will do the functionality of this flip flop. Mm-hmm. 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 Let me just recheck the solution that I have made. Maybe I made some mistake. Mm. X bar plus Y. I think this is the correct answer. X is equal to 0 and Y is equal to 0. And X is equal to 0 and Y is equal to 0. X is equal to 0 and Y is equal to 0 and X equal to 1, Y is equal to 1. It will always lead to 1, 1. So toggling will happen, right? So it's Q and bar. So what happens in the JK flip-flop when J is equal to 1 and K is equal to 1? So that's happening right now. So X bar equal to, so put XY equal to 0, 0. You get J equal to 1 and K equal to 1. Put XY equal to 1, 1. You get J equal to 1, K equal to 1. So toggling is happening, right? So toggling is happening. What is the toggling? Toggling is the opposite of previous state, right? So that is the essential functionality that is happening. So you are right. I don't know what got you confused. So you are saying J is equal to X equal to 0 and Y equal to 0 and X equal to 1, Y equal to 1. So you see, if you do the required this expression X bar plus Y and X plus Y bar, it reduces to 1, 1 for both the cases. Then toggling is happening. That is the required functionality that is to be done. And then the solution will change, obviously. That's right. Yeah, then the solution will change. So this is your question number 12. We did it. Now question number 13 is, suppose a 8-bit Johnson counter is initialized with the sequence 00000. In the decimal representation, what is the mean value of its counting states? So 8-bit Johnson counter will have in total 16 states because 2n number of states. So initial state is 000000000. So its decimal value is 0. The next state will be 10000000036. I think I've written 10 more. So this is 128. Now 1 will propagate, it will be 11000000. So it's 128 plus 64, that is 192. So I'll just go through these points quickly. So it is next decimal value will be 224, then it will be 240, then it will be 248, then it will be 252, then 254, and then 255. Then after that, this is 255 for the case when all of the bits are 1. Now 0 will propagate, it will be 0111. So it will be 128, then 63, then 31, then 15, then 7, then 3, then 1. So the average value will be 1 by 16 of 0 plus 128 plus 192 plus 224 plus 240 plus 248 plus 252 plus 254 plus 255 plus 127 plus 63 plus 31 plus 15 plus 7 plus 3 plus 1. And if you find the sum of this, it's 2040 divided by 16, and that thing is equal to 127.5. Option C. Now we have this another question. In a R2R ladder deck, if the input is 1011, Vref is 20 volts, then find the output voltage. So you have R2R ladder. So in R2R ladder, you have this expression V output is equal to Vref by 2 raised to power n, and V in, where V in is the decimal equivalent of the input value, and your Vref is 20 volts, n is your 4, and V in is the decimal value that we from 1011, so it's 8 plus 2 plus 1, so it's 11. So plugging these values, we have 20 by 2 raised to power 4 into 11, so it's 20 into 11 by 16. So the decimal equivalent will be equal to 13. So this the final output voltage value will be equal to 13.75 volts. So how many data and address input lines are required for 128K across 16 memory. So your address input lines, let's call that P. Your number of locations, let's call that M, and your number of data input lines, let's call it N. So you know that 2 raised power P is equal to M. That implies 2 raised power P is equal to 128K. That is 2 raised power P. 128 is 2 raised power 7 and 1K is 2 raised power 10. So 2 raised power P is equal to 2 raised power 17. That implies P is equal to 17. And your data lines is equal to 16, because in memory is written like this: M cross N, where M is your number of locations, N is your data line, so N is simply equal to 16. So we need to write N equal to 16 and P equal to 17. So option D is the correct answer. And another type of question is based on this PLA logic. So let's just write the output of, we need to find out the function f1 and f2 implemented by this figure. So AND of 1 will be equal to, this is this thing, this and this. So A bar C bar. AND of 2 is equal to A B C. You can check it. A B C. AND of 3 is equal to B bar C bar, and AND of 4 is equal to AC. Then I have this OR gate. So OR of 1 is equal to A bar C bar plus A B C plus B bar C bar. Then OR of 2 is equal to ABC plus AC, right? Now my F1 will be equal to, F1 is equal to OR of 1 XOR with XOR with 1. And you know that for a XOR table 0 0 0 1, and this is 0 1 1 0. So when one of the input is 1, output is complement. So F1 is simply equal to OR 1 complement. So F1 is equal to AB plus ABC plus AC complement, and this is equal to, we take AC common, it's 1 plus B, so this is AC complement. So F1 is equal to your AC complement, and that is equal to A complement plus C complement. Now you have to write the sum of product forms. You can easily write it. So this is 0, so it is for all the terms that contain 0, so it's 0 1 2 3. So summation 0 1 2 3, and C bar is that is the last term, that is 0 1 2 3 is already covered. 4 and 6 are the other terms, so this is equal to 4 and 6. Now for F2 I can write it like here: F2 is equal to OR of 2 then XOR with 0. So when one of the input is 0, or XOR gate simply performs the buffer, acts as a buffer. So F2 is equal to OR of 2 is equal to AB C plus A bar C bar plus B bar C bar, and this thing is equal to summation of 0 2 4 7. So F1 is equal to 0 1 2 3 4 6, F2 is equal to 0 2 4 7. So option A is my correct answer. So this is a pretty easy question, but you can expect questions like this in your exam, maybe. I'm not sure. So now the final question of today's live session, it says that in the following 3DT configuration of a DRAM cell, you need to first write a single binary digit D1 and then read it from terminal Y. Assume the parasitic capacitor is discharged. For this operation, what will be the correct polarities of W, R, and Y? As already discussed in the lectures in 3A1C when we discussed. So when you need to write anything, so what you need to do is first give this write W as high, so the polarity is high. Then you need to read, so again the read will be high. need to turn on this transistor. And now Y. So what will happen with Y? So here 1 is stored. So the moment you do the read operation, this Y will be discharged, because as discussed in 3T 1C DRAM structure, it is an inverting kind of a readout. So when 1 is stored, you get this Y will be discharged. When 0 is shared, Y will remain high. So Y will go to low. So first the read needs to be high, then the read will be high, and then Y will go to low. So I haven't given options here deliberately. I just wanted to show it in detail. So the correct answer to this was write will be high, then read will be high, and then finally Y will be low. So that three questions wrong. So sir, three questions wrong out eight assignment. How marks to get? I don't know. I'm not handling that thing. So you need to contact your Neptel team. I think marks will be auto updated there. I'm not sure. So I don't deal with that stuff. So that was all for today's live session, and this was a live session. In fact, the 13th live session of this course. This was the extra session where we recapped where we recapped questions related to every topics, and we saw some different questions today. We also saw some questions that we already solved, and we also saw some questions that were given in the assignment problems. So that was all for this course, this live session. I wish you all the best for your examinations, whosoever is appearing, and I will wish you all the best for all the future endeavors that are coming into your life. So stay safe. So thank you for joining. Hope to see you next time. Thank you, guys.